Getting back to some Juniper jncia-junos training. On juniper.net, when you look at those certifications and you look at this table, in one of my previous videos I showed that jncia-junos was listed 3 times. One here at data center, one here at enterprise route switch, and one here at service provider route switch. Well, it is no longer required for data center because data center has a specific jncia now related to it. So that's pretty cool. So now jncia-junos is only applying to the entry-level cert for enterprise route switch and service provider route switch. So I just wanted to give you that update. Another update that you will see in one of my previous videos, when you go to youtube.com/@AaronTechTalk, go to my playlists. If you get into the jncia-junos playlist, there it is right there, jncia-junos.
That's different about a verbal vacation.
Oh gosh, let's get through the ad.
The whole place to yourself.
Okay,
Hey everybody,
and then
welcome.
if you look down at this one video, I compare the previous version of the Juniper certification exam right here, jncia-junos JNO 103 compared to JNO 104. That is the current version, JNO 104. Because when you get over here and look at it, jncia-junos, down here it will tell you the exam code, JNO 104. So in this video I talk about the differences and comparing what they've added back to JNO 104. Basically what they added is this network fundamentals section. I'm pretty sure this was in a previous jncia-junos certification, the fundamentals. They took it out of JNO 103, they put it back in JNO 104. So I want to cover some of these network fundamentals. So what is a collision domain and what is a broadcast domain, and how are they different? Originally, Ethernet ran over what's known as thin net and thick net cable. If you Google thin net or thick net, it'll tell you it was a coaxial cable, and it came in 2 versions, thin net and thick net. The cable was a coaxial cable with one wire going through the middle of it, and the way that Ethernet computers connected to it was through a T connector for thin net and a vampire tap for thick net. They were pretty hard to work with, the vampire taps. They call them vampire taps because it bit into the cable, and it was this big clunky thing. I'll show you a picture of it with what's called an AUI cable that came off of it. It was a DB15 connector that connected into the NIC, the network interface card of a computing device or a switch or a router. And so these cables, these AUI cables, were thick and hard to work with. The thick net cable itself, I think it was known as 10 base 5, 10 megabit Ethernet baseband. 5 was about 500 meters, I think, that it could go. I think that is what 5 stood for. And then thin net was a thinner cable, a little bit easier to work with, that connected into a T connector that it was crimped onto. Well, excuse me, it crimped onto a BNC connector that twisted onto the T connector, and then the T connector connected into the NIC of a computer. All right, thin net was usually used for internal, thick net was used for external. To put some pictures to this, if we look at some images, there you go. There's a picture of thick net RG8 cable and thin net RG58 cable. They're both coaxial cables. There's the reference to 10 base 2 and 10 base 5. I think this was technically 185 meters, but it's, or 200 meters, excuse me, one or the other. It's kind of funny, they call thin net cable cheaper net. So interestingly, all the computers that communicated over a original Ethernet network, a 10 base 2, excuse me, a thin net or a thick net, 10 base 2 or 10 base 5 respectively, was all one collision domain. All right, I'll emphasize that A collision domain is also a broadcast domain, but an entire broadcast domain can be made up of separate collision domains. Okay? So if you Google computers connected to ThinNet, check it out. There you go. So you see the ThinNet cable, it shows it running behind a computer. What's really going on is there's a okay, so this cable right here has a terminator on the end of it. That's a 50 ohm terminator. And there's one on this side over here as well. Okay, so what's interesting, if you ever pulled that terminator off of the end, it opens the collision domain and you can no longer communicate simply by taking that terminator off of it. There is a 50 ohm, well, this is a 75 ohm. I thought it was 50 ohm. It's been a long time, folks. Forgive me. I'm getting it confused maybe with the ohm rating. No, I'm not. Look at that. 50 ohm coax, 10 base 2. So maybe this 75 ohm one is for something different. The point is, this is what a terminator looks like anyway, and it's a BNC connector, okay, but it's got a terminator thing on the end of it. You cannot make a connection on the end of it. This is where it connects into the cable. So that's those two terminators on the ends. Now when we look at the T connector, this is what connects into the computer, and this is what continues the cable going, well, let's say east and west. The cable comes out here and it comes out here. This is where it connects into the network interface card. There's a good picture of it. The cable going this way, the cable going this way, and this is where it connects into the computer. There's a picture of a network interface card pulled out of a computer, and there's the T connector, how it connects into the BNC connector on the NIC, and how the cable goes east and west, just like that. Well, there's an even better picture. It's got the cable on it. And look at this. They decided to terminate the cable right there at the NIC. You can do that, or you can continue this cable going on further to another computer. So my point in showing you all this ThinNet stuff, this was a single collision domain. Back in the day, in these ThinNet days of 10 base 5 Ethernet, it was 10 megabit Ethernet baseband, and there was something known as CSMACD, carrier sense multiple access with collision detection. So here we have a single collision domain. This is the ThinNet cable right here. This is the terminator on both ends, and these are the T connectors BNC'd to a computer's network interface card. All right, we have 3 PCs, and they're all operating on a single collision domain. So earlier I mentioned CSMACD. That stands for Carrier Sense Multiple Access with Collision Detection. Okay? What would happen is first, this computer would start to listen for what's known as carrier signal. All right? So what we would have is this computer would start listening to what's going on the wire. If it was idle and there was no electrical signal, then it would start to transmit an Ethernet frame. Okay? Now what happens if this is listening and this is listening at the same time, and they both sense there's no signal, nothing's being transmitted, they both try to transmit at the same time. This transmits, and then there's a collision right there in the middle. That's what's meant by multiple access. All right? So multiple computers can access the wire at the same time, but then comes the collision detection. So when they transmit and there's bang, a collision, they hear a raised electrical signal. It goes up higher, and that indicates a collision, and then they transmit what's known as a jam signal. they transmit a jam, it transmits a jam, and all of the computers, this one, and this one, all back off for a certain amount of time. I think it's called the exponential back-off algorithm or something like that. And so after they back off and wait for some kind of variable time, then the next one will try to transmit again and it will be successful, or maybe this one will try to transmit at the same time this one does, and then there's another collision. So at first you had one collision, then the second time you had two collisions. So if this computer tried to transmit twice, once and then twice, that's known as two collisions for one attempt. If it collides up to ... I think it's 15 or 16 times, that constitutes an excessive collision. So when you have, I'll say, if you have hundreds of computers, let's just say 300. So you have 300 computers on here, you've got a lot of collisions going on. That's when a Ethernet collision domain becomes overly busy and it needs to be what's known as segmented, all right? Now in the previous diagram, we showed a thin net network. Excuse me, I'm scribbling. We showed a thin net network with a few PCs on it. And I mentioned that when you have excessive collisions, you need to segment the network to gain efficiencies. Let me erase this little terminator there and give it a little more length, because I'm going to do what's known as add a bridge. Okay? This is a bridge, otherwise known as a switch in today's terminology. But years ago they were called bridges, and they were for bridging two Ethernet collision domains together, thus providing segmentation. Okay? At this point, you now have one collision domain and another collision domain. I'll just draw that in so that we can see it. We have collision domain. I'm scribbling, sorry about that. This is collision domain 1. I'll just call it number 1. That's our first collision domain. And this is collision domain 2. Okay? Now, we have two separate collision domains. Collisions do not propagate through a bridge. A collision, as I had told you previously, is a layer 1 occurrence. It's an electrical occurrence on this wire. All right? So, let me write that. Collision is layer 1. Now, they do not propagate through this bridge, okay? The bridge segments the collision domains into two separate collision domains. What the bridge does not do is segment a broadcast domain. Now, a broadcast is a layer 2 function. A broadcast is L2. So what a broadcast is, if you look at an Ethernet frame, which is a layer 2 construct, okay, an Ethernet frame is assembled at layer 2. It's a layer 2 protocol data unit. I'll emphasize or go back to something and say that at layer 1, these are binary digits, on and off bits. It looks just like a binary bit pattern. Okay, that's layer 1. And at layer 2, the bit pattern is put back together as it ascends the protocol stack inside this bridge, I'll draw, excuse me, and give it a different color. The protocol stack inside here, and it's not working out very well. Let me try to draw this differently. So what I wanted to show was that once the bit pattern enters this bridge, it goes up to layer 2 and an Ethernet frame is put back together. All right, using the preamble and the start of frame delimiter, the bridge is able to reassemble the bit pattern into an intelligible Ethernet frame, where it can then start looking at the source MAC address and the destination MAC address. All right, these are all layer 2 bridging functions or switching functions. So here's where I drew an Ethernet frame, a little square, and let's look at it down here in detail. What you have is you have headers, okay, header fields, and you have the destination MAC address, the source, I'm just abbreviating, MAC address in here, and various other fields, and then you have the data field, which is the user data that's being transmitted, and then you have a trailer down here. Okay, now what I want to focus on is the destination MAC address. A MAC address is 48 bits, otherwise known as 6 bytes. All right, and a MAC address of all F's is a broadcast. All right, so the hexadecimal, a notation is how we look at MAC addresses in hexadecimal, and this is 1, 2, 3, 4, 5, 6 bytes. Okay, that's a 6-byte MAC address. A Ethernet frame with the destination address of all F's is a broadcast, meaning that if this computer is sending a broadcast, this bridge will forward the broadcast. That's a function of a bridge. It forwards what's known as BUM traffic. B-U-M. Excuse me, let me give myself some space here and just get rid of this for a moment. And so BUM traffic, it stands for broadcast unknown unicast and multicast. That's what BUM stands for. BUM traffic is broadcast unknown unicast and multicast traffic. And what we usually say is a bridge floods BUM traffic. It's called BUM flooding. So any broadcast unknown unicast or multicast frame that shows up at a bridge floods it out the other ports on that bridge. Any other port other than the port it received it on gets that traffic flooded. So let's just say we had another segment on here. You know, we had another segment up here. Excuse me, I'm trying to change to black. We had another segment up here and another segment down here, and of course we have this segment that I've already drawn there. Now, if we received a broadcast from this computer, then this bridge will send it out 1, 2, 3 interfaces. It does not send it out the one it received it on. This is known as BUM flooding. Because of this, a bridge does not segment broadcast domains, but it'll extend a broadcast domain. So I told you earlier that a collision domain is also a broadcast domain, but a broadcast domain is not a collision domain. Now you can see that. Now we can see here's one collision domain, here's a second collision domain, but this is one broadcast domain. All right? And before, when we only had one collision domain, we knew that, well, that one collision domain standing all by itself is also a broadcast domain. Okay, but when you put a bridge in there, you segment those two collision. You create segmentation, and you now have two collision domains, but you also have only one broadcast domain. I will also mention that on a thin net network in legacy Ethernet, this was half duplex communications. Simplex communications, I'll start with. Simplex is the ability to only transmit in one direction. You can never transmit in the opposite direction. It's a unidirectional flow, and it is never bidirectional. An example of simplex would be radio. You can turn on your radio, your car stereo, you can listen to music, but you can never transmit. You can never send a message to the broadcaster of that radio station using your radio. That is an example of simplex communications. And so the next example after simplex communications, a step up from that, is legacy Ethernet, half duplex. In half duplex, you can send, you can also receive, but you can't send and receive at the same time. And you can't send and receive at the same time as another communicating device on that wire, which is why collisions occur, because it's a half duplex communications model in legacy Ethernet. Okay, so that's what half duplex is. Sometime later, after thin net and thick net cabling was getting old and technological advancements were continuing to develop newer styles of Ethernet, there was a hub that was developed where you could connect in single cables to computers. Okay? So each one of these was a PC with its own single cable connected back to a central hub. This hub was still a layer 1 device, and it still implemented the CSMA/CD technology. A big difference with this over traditional thin net, like we talked about earlier with computers hanging off of it, was that a single break in the cable would bring down the entire network would go down, okay? Just by one little break in the cable, or like I said before, if you removed that terminator, the whole network went down. All right, so one cable defect or break would bring down the entire thin net network. All right, now that is not the case with newer unshielded twisted pair cabling that we had in this next picture I drew. This was UTP, unshielded twisted pair cabling, in the form of Cat5, category 5 cabling. All right, they even had an older Ethernet standard over Cat3, which was traditionally telephone type cabling, Cat3. But really what you saw in Ethernet networks was Cat5. So this was Cat5, and what it was it no longer was a single coaxial cable, but rather a cable with 8 conductors. If you go to Google, type in Cat5 Ethernet cable, you'll get a lot of different pictures for a category 5 Ethernet cable. And you can see inside here there are several wires. I thought I was going to get a picture. Here's a better picture of unshielded twisted pair. It's in 4 pairs: orange, blue, brown, and green. Each pair is twisted, and there's a solid color and a striped color. So solid orange, striped orange, solid blue, striped blue, solid brown, striped brown, solid green, striped green. This other thing you see here is a string, and it is not used for Ethernet communications. Okay, so that is 4 pair unshielded twisted pair. Now, what is crimped onto the end of this cable is what's known as an RJ45 connector. And you have to crimp the RJ45 connector onto the end of this cable in order to use it. So as you can see here, it's a point-to-point cable. There's one end and a second end. That's it. It's not like the previous technology of thin net where you could tap in multiple devices, 10, 20, 30, 100, and form one long collision domain, not with unshielded twisted pair. So with UTP cabling, you have the RJ45 connector here and the RJ45 connector there. Registered jack 45, that's what it stands for. Okay, now that doesn't mean you have a single collision domain from here to here. Not with a layer 1 hub. This is a repeater. This is a layer 1 repeater hub. This is what I was working with back in the mid-90s. I was working a lot with repeater hubs, and then after that, I started seeing a lot of Ethernet switches coming around. Might have been around this same time, but anyway. With a layer 1 repeater hub, it still takes the Ethernet frame in and it sends it out all other ports. I'm not talking about a broadcast. I'm talking about at layer 1, the electrical signal. This repeater hub does not reformulate the bit pattern. I'm trying to draw a bit pattern here to show that the bit pattern comes in and goes out every one of these cables, okay? Whenever there's a transmission, it goes out all of them at layer 1, all right? The benefit to using these layer 1 repeater hubs were that these cable runs could stand alone. If you get a break in the cable here, well, it only affected this one computer. It didn't affect these other computers. Their cable runs were isolated from the fault on this one cable, and so it only affected this one computer. All right? What this type of cabling architecture also did was it set us up nicely for the next generation of networking devices known as switches. I really don't need to redraw this picture. I can just scribble this out, and I can say that a switch looks exactly like this, but it operates at layer 2, and it reformulates the bit pattern. It reconstructs it into an intelligible Ethernet frame where we start looking at destination MAC addresses. And we decide how to forward or filter traffic based on MAC addressing. As with a layer 1 repeater hub, I mentioned it still operates in half duplex mode, implementing CSMA-CD to deal with collisions. Carrier sense multiple access with collision detection. You have to have it in a layer 1 scenario. All right, so that was true about layer 1 repeater hubs. With layer 2 switches, now the collision domain was only between these two computing devices, 1, 2, the Ethernet interface of the switch itself and the actual PC. So now at that point, and combined with the fact that UTP cabling has multiple conductors, multiple wires, we have those 4 discrete pairs. You could use one pair for transmit and another pair for receive. I'll draw TX and RX over here, or RCV, receive. Now you could transmit and receive at the same time using different pairs of cabling between these two computers, thus achieving what now became known as full duplex Ethernet. This is still mid to late 90s technology. Okay, and so it's still going a good ways back, but this is the progression of things and the differences between collision domains and broadcast domains. So what this created for us was, now this is a single collision domain. This is what became known as micro segmentation. Microsegmentation was the ability of layer 2 switches to microsegment this network into multiple collision domains. These are now all separate collision domains. 1, 2, 3, 4 different collision domains for 4 different connections. So if you had a 24-port switch, you had 24 different collision domains. But as we remembered from bridges, layer 2 switches did not separate broadcast domains. So this absolutely is 4 different collision domains, but it is one single broadcast domain. Broadcast domain 1. Okay? I do want to add this one point of discussion. If you had a layer 1 repeater hub and it is connected to a router, this is a layer 3 device, and we're not talking about that too much right now, but I will say this. If you have, or even if it's a layer 2 Ethernet switch, let me put that here. Even if this is a layer 2 Ethernet switch and it's connected in like this, this port will need to be configured to operate in half duplex mode, this layer 2 switch. Why? Because the behavior of this device over here is by nature half duplex. So when you connect in a layer 1 hub, a repeater, to a switch to connect it to the rest of the network, you need to make sure this layer 2 switch interface is configured to operate in half duplex mode. Remember, I told you switches can operate in full duplex mode. So you want to make sure you configure that interface to behave in this half duplex environment. Hey, that's all I got for collision domains and broadcast domains. Thank you.